Hi everyone. Here we're going to take what we've learned about minerals and melting so far and study different types of igneous rocks and how and where igneous rocks actually form. So we're going to look at melt, how it moves, where it's going to solidify, as well as where and why we have igneous activity, and then learn how to classify and identify various igneous rocks. So remember that melt cools as it rises, so either underground or at the surface. As magma moves from deep within the earth up towards the surface, it's going to cool as it is moving away from the heat source that is the center of our earth. So if we're thinking about magma cooling, which magma would cool faster? Magma that we have underground or magma that has become lava and reached the surface of the earth. We think about that, we want to think about how far away is the material from the heat source. So magma that is underground is going to cool very slowly because it is still very warm. So it's going to take a long time for that magma to cool. Lava on the surface of the earth is going to cool very quickly. So extrusive magma, or lava, which is on the surface of the earth, cools very quickly. Generally, it is more spread out and it is exposed to more air and potentially water. That's going to help cool it much faster. Intrusive magma cools very slowly. So generally, it is that depends on the depth and also the size of the magma that's trying to cool. So if it is a very deep magma chamber, it's going to cool even slower versus a magma chamber that's closer to the surface. Because the deeper we are in the earth, the warmer it's going to be, the longer it will take that magma to actually solidify and cool down to the point where it can solidify. Then we also want to think of the size or the shape of the area of magma. A very large surface area is going to cool a lot faster. So here I have this chart. Here we have size and shape. So this sphere of magma is going to cool a lot faster than this very, very large sphere of magma. Same thing goes for shape, where we have a flat, more spread out, much higher surface area of magma, like this pancake shape here. This is going to cool a lot faster than magma that is in a tight ball of a sphere like this. So groundwater can also influence cooling of magma. So if there is groundwater around and available, that will help the magma cool a bit faster. So remember that we have extrusive and intrusive igneous rock. So where that rock is forming tells us if it's intrusive or extrusive, and also how quickly it's going to form. So here we have our magma chamber deep under the earth. It is a very large blob of magma. It's going to cool very slowly. It is underground. It's closer to that heat source, which is the center of our earth. It's a very big, round magma chamber. This is going to take a long time to solidify into rock. However, there are these little spindles here of this magma. This is going to cool a little bit faster than the rest of the magma chamber because it is further from the large amount of magma. It's a more spread out area. These sills and dikes, as they're called, are going to cool a bit faster than the magma chamber itself as a whole. Cooling much faster than either of those examples would be the lava that has reached our surface. So here we have a thin flow of lava down the side of this volcano. That's going to cool quite quickly. And then here we have some tiny drops of magma that are bubbling up. Those are going to cool almost immediately because they're quite small and they're on the surface of the earth. So we talked a bit about fractional crystallization while we were talking about minerals and melting. Remember that the formation of our igneous rock follows Bowen's reaction series. So what is available in our igneous rock is going to or I should say what minerals form in the igneous rock, tells us a lot about how that rock formed. Remember that the mafic minerals are going to crystallize first as that rock is melting. The felsic minerals require a lower temperature, so the felsic minerals are going to crystallize last. They need a much cooler temperature magma for the felsic minerals to crystallize. So here is the chart that I have shown before, showing the sequence of production of minerals with cooling. So here we have ultramafic minerals at the top. These are the first minerals to crystallize and the last minerals to melt, all the way down to our felsic minerals, which are the last to crystallize because they require a lower temperature, but they are also the first to melt. And here we have this step-by-step diagram showing our mafic material, our mafic melt, I should say. So here we have our magma. As it begins to cool, our mafic minerals are going to start to crystallize out, leaving behind a more felsic lava. As the magma continues to cool, we will have eventually the felsic minerals able to crystallize out. So here are some photographs of extrusive igneous rock. So here we have a lava flow. Here we have a very, very large wall of extrusive igneous rock. You'll notice that these little dots up here are people to show you the scale here. Here is about a golf ball sized fragment of igneous rock. That was probably a bubble of rock that, a bubble of lava that exploded out of the volcano and solidified almost immediately. Here we have some other things that can erupt extrusively from a volcano. We call pyroclastic flow and ash cloud, which I will talk about later in the course. For intrusive components of our igneous rocks, we often will see what we call these intrusions. So this is where our igneous rock intrudes into other rocks. So tabular intrusions, we have both sills and dikes. So a sill is where the intrusion is laterally parallel to the surface of the earth. A dike is where the intrusion is upwards or downwards, perpendicular to what the sill would be. So here we have, they're both intrusions of magma. So when it solidifies, we're going to have a sill of igneous rock. So we have this igneous rock intrusion into the previous rock layers. So we also can have what is called a laccolith. So a laccolith is an intrusion of igneous rock or magma that is between layers of rock. So here we had some magma intruding upwards, and it ends up forming this dome because it cannot reach all the way to the surface, and it ends up actually doming upwards. So it accumulates kind of a contact lens shape here. As it accumulates, the rock layers above it will also lift up. So this can cause some hilling or doming on the surface of the earth because that magma is accumulating in this laccolith. This can also then solidify into solid igneous rock laccolith shape, which will also solidify that dome on the surface of the earth. You will also, in this class, hear a lot about plutons and batholiths. So a pluton is a cooled magma chamber. So when that magma chamber finally cools, we know it's going to take a very long time. We would call that a pluton. So that would be intrusive igneous rock, but it is considered part of a pluton. Where we have a chain of plutons, we call that a batholith. So a batholith is where there was a chain of magma chambers that all solidified, is now completely igneous rock. We would have a batholith. And then here from this batholith, there was also a dike and a sill, which have since in this diagram also cooled into intrusive igneous rocks. So Intrusive igneous rock always forms underground, so how do we ever see it? If it's underground, why do we know about it? Why do we need to know these different words? Batholith, Pluton, intrusion, sill, dike. Why are we looking at these if it's all underground? That's because our igneous rock can form, and over time, it can be brought to the surface. And what I mean by that is over time, erosion can erode away what was on top. So here we have, at time 1, for example, here we have some volcanoes. There's a lava flow from this magma chamber. The magma chamber is erupting, creating this volcano. Here's the second magma chamber that's actually causing a laccolith, so you can see the doming on the surface of the Earth due to that accumulation of magma there. Over time, all of this magma has solidified into intrusive igneous rock. So here we have our plutons. This is our batholith here. The sills and the dikes are completely solidified. The laccolith is still mostly underground, but we see the chamber of that volcano still exists. We can also see these dikes here. So this was a very large dike that now that the volcanoes are gone, we can actually see that intrusive igneous rock at our surface. So if we go through even more time, you'll see that all of this has been eroded away, and now we are left with just the solidified plutons, so the solidified batholith. So we just have these really nice, rounded, very also large areas of intrusively formed igneous rock. So that is the solidified magma chambers that solidified, and over time everything else eroded away to the point where these are actually on our surface. So even though intrusive rock is formed underground, all of these features are all formed and solidified underground. They can then, over time, be shown at our surface due to erosion of everything else around it. So we do often see evidence of our intrusive igneous rocks and the way that intrusive rock can be formed at our surface. For example, we have quite a few exposed batholiths in California. So the Sierra Nevada mountain range is actually all exposed batholith. So you'll notice that these mountains are not particularly pointy. So if you were to compare this, say, to the Himalayas, they're not as tall, but they also are significantly more rounded. That's because all of this rock actually formed and solidified underground from large magma chambers. So now there has been enough erosion that this is actually the surface of our Earth. So the Sierra Nevadas are all used to be magma chambers of very large batholith that has since solidified and then been exposed at the surface of the Earth. So when we're looking at igneous rocks, one of the main things that we want to look at when we're trying to identify is texture. So texture, we're looking for, does the rock have a crystalline texture where it looks like these minerals grew together? Does it have a fragmental texture where it looks like it was mixed together, like something like cement? Or does it have a glassy texture where it looks like a glass? We also want to look at, is the rock fine-grained, meaning it has teeny tiny little grains that you can't really tell apart, or is it coarse-grained, where you can see the individual minerals? So in this granite, you can see the hornblende, which is black, versus the quartz, which is the white. So you can really clearly see the different mineral pieces in these coarse-grained rocks. The fine-grained rocks, you can't exactly point out different mineral crystals. So you'll also notice that we look at felsic, intermediate, or mafic, or ultramafic when we're looking at identifying igneous rocks. So when we look at crystalline igneous rocks, meaning crystalline means that it looks as if the minerals grew in that rock directly from a magma like we've been talking about. So these minerals clearly grew all together as this rock was solidifying. So we see that the rock is made of many different minerals and different grain sizes of minerals. So sometimes for our fine-grained igneous rocks, you can't see the individual mineral pieces, whereas in the coarse-grained rocks, you generally can. So you can see, oh, here's some black mineral, here's some white mineral, here's some pink mineral, for example. And then each type of igneous rock, felsic to ultramafic, is going to also determine what minerals you're most likely to see in your rock. So we can also have glassy rocks. So glassy rocks are not crystalline, so you can't see the individual minerals. So obsidian is a glass. Obsidian is, it does look like a glass. It's pretty much always black. However, two other tricky minerals that are also considered glassy are scoria and pumice. So they're both very, very light, have a lot of air in them. They would have cooled incredibly quickly. So if you remember, when we are forming a glass, it means that the mineral cooled so quickly, or the rock cooled so quickly that no structured crystalline lattice was able to form. So it is not going to have the mineral pieces that we would see in a crystalline rock. So the three main glassy types of igneous rock are pumice and scoria and obsidian. So pumice and scoria are very, very light in terms of weight. You can see here, this is on a dollar bill. If you've ever gotten a pedicure and you've used a pumice stone, that is what this rock is. Often pumice and scoria are volcanic eruptions where the lava solidifies right away, very, very, very quickly. It can often happen where the lava meets water. So in Hawaii, for example, when the lava flows into water, it's going to cool incredibly fast and going to form something like pumice or scoria. We can also have pyroclastic igneous rocks. So pyroclastic igneous rocks are generally from an explosion. And here is what we have. These are two examples of tuff and breccia. So these explosive eruptions can often cause a fragmented texture. And what I mean by that is it looks like different pieces of rock were mixed together and then re-solidified. So here it's not that we have individual mineral grains growing like we did with the crystalline igneous rocks. Here it really looks like here is a piece of rock, here is another piece of rock, here is another piece of rock, and they're mixed together and stuck together with some kind of cement. So this can often happen in very, very explosive eruptions where we have a lot of debris exploding out of the volcano that can fall together and then become re-solidified as one rock. So this isn't like a cement, but it can have more of a cement-like look than a crystalline or a glassy igneous rock would. So here you can see there must have been a very explosive eruption here for all of these different shards of other rock to form together in this volcanic tuff here. So when we talk about igneous rocks, we can think about where are we going to find them. So now we know to look at the texture and the composition of our igneous rocks. So where do we find them? The answer is everywhere that we have volcanoes. So subduction zones, mid-ocean ridges, continental rifts, and hotspots are all going to create igneous rock because remember, any solidified magma or lava is an igneous rock. So here we have our subduction zone. The subduction zone the Aleutian Islands in Alaska. This is where we have our flux melting here as this oceanic crust is subducting underneath the continental crust. This melting is going to rise up, solidify at this volcano, causing igneous rocks. Mid-ocean ridges, of course, is that underwater mountain range at our divergent boundary, creating more and more ocean crust as this seafloor spreading continues. So you'll notice that our oceanic crust here that's being created by our mid-ocean ridge is an igneous rock. It's actually called basalt for the most part. So something else to note is that at the mid-ocean ridge, the rock that is formed is going to cool very quickly. Even though it is underwater, it's below what we call sea level, we still consider it to be at the surface of the earth, so that is still an extrusive rock. So mid-ocean ridges, that magma that reaches the surface to create our ocean floor, is generally basalt, and that is an extrusive igneous rock. Even though it's not technically above sea level or on one of our continents, it is at the surface of the earth. We also have continental rifting. So remember that decompression as this magma gets moved upwards. The pressure is going to change. It's going to cause melting. So as these continents are moving apart, we will have melt here. That melted rock, once it solidifies, is igneous rock. And then, of course, hot spots. So Hawaii, for example, where we have that magma plume, if it solidifies parts of it underground, that will be intrusive igneous rock. Anything that reaches the surface from those volcanoes will be extrusive igneous rock. So here is an example of some rocks that you might actually find on Earth, matching up with where they are in this diagram. So here we have our intrusive rock. Our intrusive rock is going to have much larger mineral grains. So remember that intrusive rock cools very, very, very slowly because it is still closer to that heat source. So our intrusive rock is going to have those larger clasts, those larger mineral grains, because it takes a very long time to cool, meaning that that rock, that magma, has a longer time for the minerals to grow. So that very long time that it takes to cool allows for the mineral grains and the mineral crystals within that rock to grow to larger sizes. So granite, for example, has generally very large mineral pieces within it. That is because it cooled underground. That time that it took to cool allowed for the minerals to grow into very large, visible pieces. Extrusive rocks, for example, rhyolite and basalt, you're going to see very fine-grained because the extrusive rocks cool much slower. So you're not going to see the large mineral pieces that you would from an intrusive rock because it didn't have enough time. So extrusive rocks, we still have minerals within them, but they aren't going to have the large crystal sizes that we see from a rock that cooled much slower. And then rock from an explosion that cools almost immediately is going to be either an ash or one of our glassy rock types like pumice. So a big difference between our intrusive and our extrusive rock are the texture. So where we have those large grain sizes, the coarse-grained rocks where you can clearly see the different pieces of mineral, you know that that rock cooled underground. It took a really long time to cool, and that's why the minerals were able to grow so large. Whereas where you see rock with very, very fine-grained, you can guess that was an extrusive rock that didn't have a long enough time for the minerals to grow very large. So that should help you in identifying your igneous rocks.